Welcome to Maths with EJD. In this video, we are talking about data preprocessing under the broader topic of data in the time domain. And of course, the playlist is on spectral analysis, which we have seen to be that tool that helps us to, transform data in the time domain to frequency domain. So we can see things like frequencies, amplitudes, phases, and all of that. Okay. So data preprocessing in time domain would be what this is about. And of course, like I've been doing for the other videos, I think I want to put, uh, when I make it into a PDF document, I want to be able to see the overall topic. So the best way to do that is to do it this way right now. Okay, so data preprocessing in time domain is the topic once again. So let's get introduced to the concept. Data preprocessing is a crucial step in signal processing. Of course, I mean, I work with data a lot, ranging from Microsoft Excel to Python and all of that. And I have playlists dealing with these different aspects. So I think I have about 45 videos on Microsoft Excel or something like that. Then I have 60 videos on data science. I have a couple of videos too. I mean, several videos, I think, on data analysis. Then I did SQL too with maybe 11 or 17 videos. I'm not sure the number now. If I let, I can check my channel right now. So just go to YouTube and then, okay, I just come here and then I do view my channel. And then from there, so I have the playlist right here. Okay, I have okay, I'm just building spectral analysis. I'm still on Python Basics with CJ, 16 videos already. I still have more to go. I think it's going to be more than 20 videos for this. Then okay, YouTube, Microsoft Excel, I have 45 videos. For data science, I have 60 videos that's talking about machine learning, basically. SQL 11 videos, data analysis with Python 35 videos, like that. So you want to explore this thing, especially if you're new to the whole idea of data. You can start with Microsoft Excel. So from there, you can then move on to the next thing, natural thing to move on to is maybe Python basics. So once you learn Python basics, then that can help you to understand data analysis with Python, then SQL with Python, and then you can go all the way to machine learning, depending on what exactly your desire would be. Okay, so data preprocessing is a crucial step in signal processing. Now, data preprocessing is, I mean, for any kind of data thing you do, getting data and preparing the data, pre-processing it. I think we call it data cleaning or data cleaning or data cleansing or data preprocessing, whatever you want to call that, or data preparation. So those are the words. In fact, that seems to take the bulk of the time for data analysts, right? So to get the data in the right shape for analysis is really important. And it is no less useful when you're talking about signal processing under the broad idea of spectral analysis. So the goal is to prepare raw signals for analysis, ensuring they are clean, centered, and scaled, minimizing distortions or biases in further processing. So key processing steps include detrending and demeaning. All right. So detrending and demeaning go together. Then you can do windowing and signal normalization. So these are the four things we'll be doing as far as signals are concerned. I mean, for normal data, right? I mean, not regular data that outside of spectral analysis, some of the things you do is you want to you want to remove inconsistencies. You want to, of course, we also get to normalize data by using scaling and things like that. You sometimes you also want to remove you want to deal with outliers, right? You want to deal with outliers. You want to remove duplicated values. You want to fill up missing values or delete them altogether, depending on whatever you care to do. But in the case of signals, the trending and the meaning is one thing, windowing is another, signal normalization is another, and that is what we are here for. So let's look at the first kind of thing we want to do here. That's talking about the trending and the meaning, right? So the trending removes slow varying trends in the signal that are not of interest. So any slow varying trend in the signal that are not of interest, the trending helps to remove them. So trends can distort spectral analysis by introducing low frequency components. So low frequency components are usually not of interest to us in this case. Since we are talking in the frequency domain, right? So the mathematical formulation of this will be this. So for a discrete signal x of n of length n, right? So you want to fit a linear trend using least squares. So you say x trend of n is an plus b, a simple line where a is the slope and b is the intercept. And then you can then subtract the trend. So x detrended now of n is xn, the original discrete signal, minus the x trend, which is an plus b. That's what the trending is all about. So if you look at a very good example of that, imagine you have, of course, we import numpy, then we need scipy.signal. Scipy is numpy, matplotlib, and scipy are libraries in Python that are NumPy is good for numerical Python. SciPy is good for scientific Python. So you can see when we talk about the idea of signal and the trend now, it's coming from scientific Python. So it's good for scientific computation, basically. All right. So here now, all this. Okay, let me just do it to fit into the frame exactly as much as possible so we can see everything together. All right, so here, so after importing all these three libraries now, so we generate a signal with a linear trend. So you have n is NPR, we are taking, so since we are dealing with, the whole thing is discrete. That for discrete, we talk about whole number. So we are taking from 0 to 100 for uh, the number of discrete points, right? And then the signal now is 0.05 multiplied by whatever n is times sine of n pi 0.05. Normally t, but now n is taking place of that because we're dealing with discrete signal. We talked about different types of signal in, I think, in the second or third video, most likely the third video. Yeah, the first video under data in time domain. So we talked about different types of signals. So we can have discrete and continuous. We can have stochastic and deterministic. We can also have stationary and non-stationary, like that. Okay, so here we're talking about discrete data. So to detrend this signal now, what do we do? So we say signal detrended is now the trend signal. So this detrend is actually a function inside of scipy.signal. So this is the signal defined in line 9. So we detrend that signal. Then so you just say plot. So this is the key job we're now doing here now. Plot now. So you're plotting the signal. So this signal now, you're plotting it against n, all right? And then that's the original signal. On the other hand, you're plotting the trended signal, okay? So you're plotting the signal, the trended, against the n. So you can see how it happens. So here now we now see the trended signal. And then we do the plotting. So I've done Control Enter. So it's more or less like pressing the play button here. And it takes a bit of time the first time you're running. And then once it's all done, so you see, so this is the graph. So the original signal is this one now. So after we have removed we have detrended the signal, we now have something like this. So you see, so this makes a bit more sense because we have removed low frequency signals and things like that is making it unnecessarily. It's more like removing dead, filtering out the noise or something like that, from a signal. That's the kind of the idea the trending talks about. And then we can also talk about demeaning. So demeaning removes the DC component, which is the mean value from the signal, centering it around 0. Okay. So here to compute the mean, now we have, of course, mean is x bar equals 1 over n, summation from 0 to n minus 1 of xn. That's average, basically. And then you subtract the mean. So the demeaned value of n is now the original signal, the discrete signal. Then you remove the mean value from it. That's the idea of demeaning, right? So to do that, that's easy. So first of all, we are doing it by generating the same signal as the detrending example we had up there. Okay, same thing, but the only thing now is that we have the signal. So this is the signal itself now. From the signal, we now have NP minus mean of the signal. So from the signal, remove the mean of the signal. That's demeaning, removing the mean of the signal from the signal. That's what that is. And then we plot that. So we have the original. Okay, I think these are the two key things that are happening here. Then I can space this out, right? So that goes. And then here now, so for the demeaning, it's simple. Signal minus mean of signal. That is the meaning of the signal. And then I can run the play button or do Control Enter or Shift Enter. And then here, so we remove the mean value. So we have this whole thing going like this. But then what if we actually use we generate a signal with a DC offset, okay? So signal with mean offset. DC is mean, as we saw up there. So so the n now is we pick a range from 0 to 100, and the signal now we have 2 plus np sine 2 pi. So as opposed to what we had previously, so you see up here we just had 0.05 n. The 2 plus is not there. Okay, so here we have 2 np sine something. So signal with mean offset now. So I guess the 2 will be the mean offset apart from the signal itself. So when we demean this kind of signal, see what happens. So then we plot the signal against n, and then the mean signal also against n. Of course, n is what you have on the x-axis, and then you have, I think the amplitude is what I can say on the y-axis. So we do this again. So you see, this is the original signal, and this is the demeaned signal in this situation. Okay, that's a signal with mean offset. And then we move on to, so what are the things we do in preprocessing data? We detrend, we demean, and then the next thing is windowing. Okay, we can window the data. So windowing concepts. Windowing is applied before frequency domain analysis like FFT to reduce spectral leakage. So if you want to reduce spectral leakage, so detrending removes trends, right? So if you want to reduce spectral leakage, you can use windowing, which occurs when non-integer cycles are analyzed. So if you're analyzing non-integer cycles, you can use windowing to reduce spectral leakage. Okay, so the mathematical formulation is such that x windowed n, okay, of xn is the discrete signal, but x windowed n is now the windowed signal. And the formula is simply the original signal multiplied by the window function, w of n, where w of n is the window function. And then we have different window functions. We have a rectangular window function where w of n is equal to 1. I mean, so you're just multiplying whatever you have by 1. So rectangular window keeps the signal the same, basically, and n lies between 0 and n minus 1. Then you have the Hanning or Han window. So that's W of n is 0.5 into 1 minus cos 2 pi n over n minus 1. Okay. And then you have Hamming window, which is 0.54 minus 0.46 cos 2 pi n over n minus 1. And then you have the Blackman window, which is 0.4 minus 0.5 cos 2 pi n over n minus 1 plus 0.08 cos 4 pi n minus 1. So, I mean, all this, so these different windows can be tried out to see what we get. So, Python visualizing, this is where things get more interesting. So imagine we're doing windowing for a signal, right? And what we are so here now you have SciPy, of course, and from SciPy to signal you're importing windows, different windows available. So you import matplotlib as PLC for plotting, NumPy for numerical Python. So we have n as 100 here now, for the signal. So you see, we keep seeing all this n minus 1, n minus 1 here. So that's actually the value of n that we had seen before. Okay. Right. Yeah, I think we've seen that a couple of times. So length n. So that's the length of the signal. Okay. That's the value of n. So we have okay, I've come too far. Yeah, good. So here now, n is 100. That's the length of the signal. So for the rectangle signal, we have windows. This windows now, we are windowing. So window.boxcar n, that's for rectangle. Han, we have windows.han of n. That's for 100. Now, Hamming, windows.hamming of n. Blackman, windows of Blackman of n. And then we can now do all the plotting. So for rectangular window. So we have that's rectangular. We have Hanning, we have Hamming, we have Blackman. And then we just plot all of these things to see how they all behave. Okay, so you see the rectangular window, nothing changes because it just remains the way it is. Nothing actually changes. And then, of course, this here talks about the length of the signal. And I want to believe this is amplitude on the y-axis. So for the rectangular, it just remains the way it is. And then the next thing is the Hamming is what follows, this green one. And then you have the Hanning. The Hanning follows, of course, the orange, and black one is the red one, like that. So those are the window functions. So those are, apart from rectangular, the other three, they have some closely related kind of behavior, right? Okay, so we can also talk about another preprocessing thing is, we talk about demeaning, detrending, demeaning, windowing, and normalization. So let's talk about signal normalization. So normalization scales signals to a standard range. So, I mean, even in data analysis, normal data analysis that I taught, I did something about normalization there. So normalization scales signals to a standard range, improving numerical stability and comparability. So I think it's also it follows the same kind of idea where we get Z-score in statistics, right? So types of normalization, we can have a min-max normalization. So X normalized mean. So we have X n minus min-max. So max X minus min-max. So it's more like you want a minimum and maximum kind of value. So you set the minimum and maximum value, and then you use the formula. Then you can have the Z-score normalization, which is, you have normal X minus mu over standard deviation. So that's Z-score normalization, where mu X is the mean and sigma X is the standard deviation. So that's the kind of thing we do in statistics. And then you can have the unit norm normalization. So you have X norm n is now X of n over the absolute value of X, for the unit norm normalization. Okay, so we can visualize all these things here for normalization. So you import numpy, import matplotlib, and then it generates a sample signal. Since we are talking about discrete stuff now, so from 0 to 100, and then you have the signal 5 sine 2 pi 0.05 n, then of course you pick your n from here. So this is signal with offset and amplitude. So we have amplitude here is 5, the offset is 10. The offset is more like the DC offset. That's the mean offset, like we saw previously. Okay, and then we have the Z-score normalization now, which is signal minus mean of signal divided by standard deviation of signal, and this is the signal right here. And then you can plot original and normalized value. So we do the plotting for the original signal against n, and then we have the normalized signal, which is the normalized signal is seen in line 11. So we plot that against n also, and then we do all the whole labeling and all that. So we have the sample index on the x-axis, and the y label is amplitude as usual. So here we have all of that. So here, this is the original signal, and then the normalized signal. So the benefit of normalization is that it prevents large amplitude signals. Okay, it prevents large amplitude signals from dominating analysis and makes signal comparable across data sets. So look at all these big amplitudes here. Now, after you normalize, things are a bit, things are within a particular range that can make a bit more sense. Now, instead of, all along we've been using signals that are in formula form, which are clearly time series things, by the way. But then I chose now to use data set. So, I mean, the data here I actually imputed directly, or you can actually maybe upload the data. Maybe I would, in another situation, I can, get a data set uploaded, and see how we can call a data set from somewhere and then use here. Especially since I'm using Google Colab, most likely you can upload the data set to Google Drive and call the data from Google Drive to Google Colab so you can run the data set. So I'm working, what if you want to work with raw time series data, for instance? So imagine we took some measurements, maybe maybe this can look like, okay, these values look like temperature in some very cold regions, for instance. So imagine you took 50 temperature, maybe a daily average temperature for 50 days, for instance, if for let's just assume. Then we have this time series data for those 50 days. Of course, we don't need the time series part because we know it's 50 data points. So that's like, it's either you're taking, if you can say 50 seconds, I mean, every second for 50 seconds, or 50 every hour for 50 hours, or every second for 50 seconds, every minute for 50 minutes, every hour for 50 hours, or every week for 50 weeks. I mean, whatever time duration you're interested in. So in short, we know we have 50 data points for a time series data. So in this case now, so all along we've been seeing signal as something, maybe 5 sine something by frequency times time or something. But here we have just data, right? And that is exactly what this is. So here, so you have n now is np dot a range of L. So that's the length of the signal, talking about the 50 data points. So that's the value of our n, of course. So we need to do the trending, right? So we just say, for in line 17, we say signal the trend that is equal to the trend this signal, okay? So the data set is now the signal, right? So that was the analogy I've made from the beginning. So you can, in place of signal, you can have a data set. And then demeaning, so signal demeaned can now be signal detrended minus the mean of signal detrended. Okay. Then, so before you demean, right? So you demean a signal, then you now detrend you now demean you detrend the signal, then you now detrend. I mean, you now demean the detrended signal. So I didn't do that when I did the first example. So pay attention. So you detrend first. So after detrending the signal, you now demean the detrended signal. That's the way it should go. So you remove trend first, and then you now remove the mean. That's what the way it should go. And then for the windowing, if we use handing window, for instance, we just say hand window, windows.hand, the length of the signal demeaned. So you now have signal window. This now signal demeaned times hand window. You know, that's the signal times the window function, right? Here we're using hand window. Okay. So we also have normalization. So you have signal normalized equal signal windowed minus mean of signal windowed divided by standard deviation of signal windowed. Okay. So you now plot all steps now. Plotting steps now. So you dimension the figure 12.12 by 8, and then we are going to have 2 by 2. So that's 2 rows, 2 columns. The other time we had 211, I forgot to explain that. 211 means you have two rows, 1 column. So you're going to have one graph on top of another. But 2 by 2 means you have so you have 4. It means 2 by 2. That means you are going to have 4. So you have 2 figures in 1 row, and you have 2 figures in 1 row, making 2 rows. So that's 2 rows, 2 columns of figures. That's what this 2 by 2 means. So the first one now is going to be the original signal. You know, the 50 data points that I talked about. You have the original. The next, you're going to have the demeaned signal. Of course, after you detrend, you demean. So that's why that is going to be together. So the title of that is going to be the detrended and demeaned signal. Like I said, you have the signal, you detrend it. After detrending it, that detrended signal, you now demean that. That's how the meaning goes. Okay. Then you also have the windowed signal for using Hanning window. And then you then finally have the normalized signal. So again, you can come here and run it. So as it keeps, once it finishes running, it shows you the plot. Okay. So you have the plot right here. So showing us the original signal. That's the 50 data points we have. And then we have the detrended signal. And well, this is not looking like temperature, because I mean, temperature should be falling and rising, right? Maybe it's something else, but I mean, it's just some made up data, by the way. So, but if you have actual data, you can try this out. So you can have detrended and demeaned signal like this. Then you can have the windowed signal, which is handling in this case. You can try other types of window functions. Then you can normalize the signal. So this is what that comes to, the Z-score normalization. So I also did the same thing for 100 data points. Okay. So exactly the same thing. So I won't have to worry about going over it. So I run this, and in no time we have the results jumping out like this. So compare. So the more data you have, the more behavior you should expect, I think. So we have the original, everything is clustered together. So this is a growing trend. So it's not looking like temperature data, by the way. It could be whatever. And then the detrended and the mean signal, you see it like this. And then the windowed signal using Hanning window is like this. Normalized is like this. So finally, we come to the summary of what we've been talking about data preprocessing in time domain. So preprocessing step, detrending, this removes Detrending removes slow trends. In this case, you have the signal minus an plus b. That's the this is the trend being removed. That for demeaning, it removes the DC component, which is the mean component. So you have the signal minus the mean of the signal. Then windowing, this reduces spectral leakage. So where you multiply the most likely not the signal directly. Since if you have demeaned the signal, then this will be the demeaned signal multiplied by the window function. And then you have normalization of signal, which helps to scale signals, to put it within a particular range for easier, for better results, right? So, and that you have the signal, most likely the mean signal or the windowed signal or whatever you choose minus mu all over standard deviation. I think the normalization we did here was with, what was it with? With the normalization we did was on the, let me see, it was on the signal, the windowed signal, exactly. So you detrend. So whatever you detrend, you now the same thing you have detrended, you demean. So whatever you have demeaned, you window whatever you have window, then you normalize. So that's the step you go in. The trend, the mean, window, and normalize signal or data set in time domain. So with this, we come to the end of this interesting video. Let me know how helpful this video is for you. And if there's something else you'd like me to try out, feel very free to let me know as we go on in this journey, talking about spectral analysis. I mean, so far it's been very interesting for sure. Even for me, it's really sweet to make these videos because I'm learning new things myself. Okay, so if you have subscribed to this channel already, thank you very much for that. If you have not subscribed, of course, you know you'll be missing a lot. So you want to go ahead and subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. Uh, so you can always go a step further by joining this, by becoming a member of this channel. So that brings you into some closer relationship. I can share my PDF notes of some of the things I've taught here, and we can have one-on-one interaction depending on your level of membership. All right. So ultimately, don't forget to like, share, comment on Facebook, on YouTube, wherever, so that we can share ideas together, and so that more people can have access to the great content I have going on here. Till I come your way again, keep doing this analysis, this type of analysis, right? Maths, Python, data, keep doing all of them right. Bye.